Okay, people, 12.5, 12.6, 13.1, questions about the exam one review. What questions do you have for me?
Um, 1436, 12.6.
12.6, 36. 12.6, 36. Reduce the equation of one of the standard forms, classify it and sketch it. So let's do 37 since it's the same sort of idea. Okay, so 37. The equation in question, x squared minus y squared plus z squared minus 4x minus 2z equals 0. So when it says reduce this to one of the standard forms and classify it, I go back to that list of the 6 on page 837. And I'm trying to figure out which of those pictures this is. An ellipsoid, a cone, an elliptic paraboloid, a hyperboloid of one sheet, a hyperbolic paraboloid, a hyperbola of 2 sheets. So I look at those standard equations. And I say to myself, what could this be? I've got x squared and x, I've got z squared and z. I'm going to do completing the square. So let's start there. I don't have to do anything with the y squared, that's fine. But let's do x squared and z squared. And I get half the middle term squared, that's going to give me a plus 4 here. Half the middle term squared is going to give me a plus 1 here. If I add it to the left, I have to add it to the right. So I have x minus 2 squared minus y squared plus z minus 1 squared equals 5. And now I go look at my standard equations. And my standard equations fall into 2 main categories. The ones that have a constant alone in them and the ones that don't. There's a number here equals 1. There's no number here. If I were to put it all on one side, it'd be equal to 0. There's no number here, be equal to 0. That's got an equals 1. That's got an equals 1. That doesn't. So I'm sure that what we've just drawn is either an ellipsoid, hyperboloid of 1 or 2 sheets, because it's got a constant. So now I need to know which of these 3 it is. But in all 3 of those, the constant's a 1. So I'm going to divide by 5. X minus 2 squared over 5. Y squared over 5. Z minus 1 squared over 5 equals 1. Now, with a minus sign in there, if they were all pluses, that's an ellipsoid. Or in this case, it would be a sphere, right? If they were all pluses, because all of the numbers on the bottom are the same. With minus signs, this is a hyperboloid. So now I go count. And I say to myself, hey, in that, they're all plus. In this one, there are 2 minus signs and 1 plus. In this one, there's only 1 minus sign. I'm in this case. Now, in this one, the z is the one that's negative, and our hyperboloid is aligned along the z-axis. Its circle part is in the z direction. So I think I'm in this setup, but the minus sign's on the y, not z. So I think this is a hyperboloid, but instead of going up and down, it's going left to right. Technically, it doesn't, but like when we did all of our hyperbolas and ellipses, we were in the standard form, we always wrote them equal to 1. Hang on a second. Let's check and see if I'm talking out my ass or not. So I want to graph this. Let me open the grapher and share it. So I open the grapher, 3D, standard white background. Go back to Zoom and share this so you can see it in the recording there. And now I go in and I'm like, okay, let's get rid of that equation and type in the equation we started with. X squared minus y squared plus z squared minus 4x minus 2z equals 0. Yep, that's a hyperboloid. Notice its center is not on the axis because we shifted over by 2 and up by 1. So the point 2, 1 is the center of this hyperbola. But there's the y-axis, and our circles are going in that direction. If I zoom out a little, I'll get more complete circles, but there are my hyperbolas. Okay. Why does it have to equal 1? Technically, it doesn't. But let's go back to the equation for a circle, right? In a circle, we have x squared plus y squared equals r squared. Yes? So if I divided by r squared, this would be x squared over r squared, y squared over r squared equals 1. Yeah? So really, I can write every circle with the right-hand side equals 1, not the radius. All an ellipse is a circle that's distorted. So if I change these two numbers, and they're not the same anymore, then I get an ellipse. But that's really just a modified circle. So why do I write it equal to 1? I'm going to go back to last class, to Calc 2, and think about parametric equations again. What's my easiest parametric equation for the unit circle? Cosine of t and sine of t, right? And the unit circle is the equation, this, but it's really this equation, cosine squared t plus sine squared t, and that is 1. That's the way we defined it. So if I think of this really as a variation on parametrics and trig functions, that's why we end up with 1 all the time. Because it's really trig hiding inside of all of this. And where ellipses were added to make it kind of like a circle, a hyperbola is subtracted. And so then whether we get 1 sheet or 2 sheets depends on which part we subtract after we do the rotating. So it all ends up based on 1. Yes, no.
There's kind of a similar question on 13.1.2. We have to make
13.1 number 42, where you had to make the intersection of two surfaces, right? So, which one do you want to do instead?
Is there one like that's no similar to 42?
Well, really, I think 43, 44, 45 are all fairly similar.
It's just because I think you had to change the X and Y equations to cosine. and sine.
I think that's easiest based on what we've got. So let's think about 42 visually before we actually do anything. So let me cheat and let me go back to Grapher. And now I'll take this equation out. And what's the first equation in 42? Before I graph it, x squared plus y squared equals 4 is a circle in 2D. But I'm in 3D, so I get. There it is. Now I'll add a new equation. Equation new. Oh, not from template. Equation new. What's the other part?
See,
Now that is not an equation that fits our standard idea, but it tells me that this is just some surface. And it turns out when I draw this surface, I'm going to change the colors on that. So let's make that solid and we'll make it blue. So it's easier to differentiate the two of them. And now I see something interesting. This blue shape, let me turn off the cylinder. This blue shape is a hyperbolic paraboloid. It's just not lined up with the axes the way the other one was. It's rotated 45 degrees. Oh, I got to go back to linear algebra and rotation matrices. I know we did this kind of. This is a quadric surface, chapter 7, section 3, 4, somewhere in that. So you did this. I know you did, but maybe you didn't get to it last year. I don't know if Dr. McNabb covered it. I know it's in the book, but all we did is really rotate this and it goes into our standard form, right? So I'm going to change this to be a little bit see-through. Oh, I changed the cylinder. Whoops. Let me go back to the cylinder. There, see how the cylinder's a little see-through there? It's a little transparent. I can see the axis in the middle. Let me do the same thing here. I'll make this a little see-through. And now I say to myself, look, where those two cross, I've got a curve. And it does this. It goes up and comes down and goes up and comes down and goes up and comes down as we go around, right? So it's really the circle in the XY plane that's been lifted to lay on this funky saddle. I go back to pictures in the textbook where we saw our ellipse and our plane. Stop share. There we go. So you see how we can describe the cylinder in cosine and sine, right? But then the z values are determined by this part, so we rewrote that to be 2 minus y. And then we took the y from the circle. Well, the z value in my new picture is going to give rise to a curve that kind of looks like this thing. So that's a circle when I look down on it, but it's got the wiggly edges, and those are changes in z, aren't they? And if they're just changes in z, I can use what we have for x and y, figure out what the z should be. And those pieces of information are right in the equations you gave me. If you tell me a circle for that cylinder in trig functions, and then you say, oh, but I want the z to do this thing, then you take the two trig functions or parametric equations and shove them into z. That's sneaky, isn't it? But the advantage is because I know what parametric equations I should use for the cylinder, moving it to be on the saddle at the same time is just taking those X's and Y's and putting them in. And that's the important part. You have to say to myself, wait, I've got a circle. So I know the parametric equations for a circle. We did that. And so I remember it. That's the problem part, Mia, right there. I remember it. And that's why all of the ones that are on things, I can describe them parametrically by saying, what does it look like from different angles? Oh, this is a circle, but now it's this funky weirdness saddle at the same time. We didn't actually build curves that way, but remember I showed you that that twisted cubic thing? The physical 3D print of the twisted cubic? I bought them again. Let me drag that back up. Here's my twisted cubic. The flat part makes it a little harder to see. Where's the one without the flat part on it? Way down here. There we go. All right. Very thin plastic, so it doesn't crash to the ground when I drop it. Here's the equation. T squared, T cubed. So if I just look at this in X and Z, I should see something that looks like a cubic equation. Right? X and Z. Y, Z equals X cubed. If I just look at it in X and Y, I should see a parabola at T and T squared. If I look at it this way in Z and Y, then I should T squared, T cubed. The hell is that? Oh, well, that means that Z is Y to the 3 halves. And that looks like a bird. So by looking at it in 3 different orientations, I can kind of play with the parametric behavior. And those 3 pictures are on page 852 in our text. And we see from one direction in just X and Y, I see a parabola. From another direction, I see a cubic behavior with X and Z. And here's that bird in Y and Z. That's messed up. But moving from 2D to 3D is visually hard. That's why I tend to draw these things in the computer. So I don't have to draw them by hand, but I still have to describe them mathematically to the point where I can make the computer actually do the building part. Better? The 3D printer that was in Boyle's second floor, which broke a couple of years ago when one of the printer nozzles got caught in the hot fiber and yanked something off the printer, hasn't been repaired or replaced yet. Hopefully it will be soon. It took me most of a summer to figure out how to graph things in 3D. And then I went pretty crazy. And I made a lot of stuff. But there's a program for doing those things. No, it's under here. There it is. Which generates solid picture files. And then you send those to the printer. Did a lot of junk. But eventually, the printer had, this part was fine, this piece was fine, but as it dragged through one of the monitor pieces, the camera that watches it got caught in the hot filament and got yanked off. And I can't fix that part. And this is a 7 or 8 year old printer, so it's not worth replacing. Buy a new one. But that's up to the School of Natural and Health Sciences because it came out of their budget. But you can build all sorts of crap. Yeah, see, that's the part that got ripped off right there. There's where the camera goes. There's the program to open it. Please open, I hope. SCAD, solid computer aided design. So over here you have, I want you to make a circle. And I want you to move it from here to here to here to here to here. Notice I'm using an inverse tangent to do the angle to go around the circle. It's it. And then I want you to make the tube go from here to here. Oh, but I want it to be t cubed, t squared. Notice I had some scaling factors in there to make it actually look nice. I put a 2 and a 0.5 in there to get information to shrink it to fit the right size. And then I just dumped it to the printer and it printed this stuff out. But it made a solid STL, solid transmit layer file. Otherwise, I would have been lost. Somebody else made the knot. I simply downloaded this and sent it to the printer. If you go to thingiverse.com, they have a whole bunch of these. And I put the twisted cubic up on Thingiverse. I said, hey, this you can do this, and if you adjust the curve, you can do lots of other stuff too. Anyhow, see, I need the trig function, then I need to say, oh, I'm going to lift that to look like this now. I have to parameterize somehow. More questions, more stuff. There's another one. From 12.5.42, which asks, find the line through each 2 points and find out where it intersects the plane. Okay. Advantage number 1. When I go to find the line through points, I get an equation in T, right? Because when I make a line, I get some vector equation. Yes? But I also have a plane. What's the equation for the plane in that problem?
2x plus y minus z is -2.
So I want to know where this and this happen at the same time. Which means this x and this y and this z need to satisfy this equation. So I can take these three things and put them in here. And then my problem becomes, can you solve for t? Once you know the value of t, you can then tell me what x value, y value, and z value make this true. And then you know that spot is where the line you built where the line you built goes through the plane you have. You find the t value, you then use the t value to find the x, y, and z point. I don't know if they're going to go through perpendicularly or at some weird angle, or maybe it's a really shallow angle, and I have no idea what the orientation is. This plane, 2, 1, -1, right? The direction vector for the plane is 2, 1, -1. 2, 1, -1. The plane should look like this, because it's perpendicular to that. That's our normal vector. I don't know what the vector for the line is because I haven't worked it out yet. But if you work it out, then you know what direction the line is going. And you'll be able to tell me where it is. Make sense? Turn an equation from lots of variables into one, t. Then you can walk away. No questions.
This question 4 is 12.4.
12.4?
Yeah.
Sure. I did post the keys to our Canvas page, but let's just do it right here. Problem 40. So this is our torque problem, right? So I have a handle, and then I have a force being applied to that handle in two different places. This is our origin. I'm sorry, that's our point P. Then we have a point Q here, and we have the top of the handle up here. And we're told that we are pulling with 20 pounds of force in a horizontal direction. I'm going to go ahead and make the origin of this system go through the point P. Now, we're also given some measurements, aren't we? There are some distances involved here. We're told it is 2 feet here from the height of P to the height where the force is applied. And it's 1 foot from P to the point where the force is applied horizontally. So far, so good? So, dumb question number 1. How far is it from here to here? So the radius has length square root of 5 feet. So far, so good? I'm gonna keep drawing that line. This angle here is the same as this angle here. Because those are parallel horizontal lines, and it's the same line crossing at the angle, right? So this angle is the same as the angle between the radius and the force. So here's a question: what's that angle? I don't know. But I do know down here that I could draw a right triangle, and then I would have the opposite and the adjacent sides. So I know the tangent of theta is opposite over adjacent, 2. But I also know all 3 sides of that right triangle. 1, 2, and you already told me that that side's the square root of 5. Torque is R cross F, which is the same as length of R, magnitude of F, cosine theta. Yeah. Cross product. Sine theta. Dot product is cosine, cross product is sine. Length here is square root of 5. Length here is 20. What's the sine of that angle? Just use the triangle. Which 2 sides? Sine is opposite over hypotenuse. 2 over square root of 5. Those cancel, I get 40. Foot-pounds. Pounds times feet is my unit. If I was in metric, this would be Newton meters. Part B says do the same thing, but now use the point Q. Same force, just instead of holding it up here and pulling, hold it down here and pull. So I'm going to draw just the part with the point P and the point Q. And I'm going to draw my force. But again, I'll put the x-axis and the y-axis through the point P, and I'll go back and I'll look at the measurements on the drawings, and it tells me that this is 0.6 and this is 0.6. Wait a minute. I know the angle. What's this angle? That was up here. I'm down here now. Right, because tangent of theta is equal to 0.6 over 0.6, which is 1. So theta is 45 degrees, or pi on 4. Hey, wait a minute. I know the radius length. Same question as before. So it'll be 0.6 squared plus 0.6 squared square rooted. But this is a 45, 45, 90 right triangle. The hypotenuse is always square root of 2 times the side length. And now I can do the exact same thing. Force, radius, sine theta. Radius is now 0.6 root 2. Force is still 20. Sine of 45 degrees. Cancel, cancel. 0.6 times 20 is 12. So in spite of the fact that this was a Calc 3 question, it was really a trig question. You rat. Trig was a long time ago, man. Almost always, my goal is to insert the origin and the axes in a useful place. And if I'm trying to measure around a particular point, what's the torque around here? That's almost always easiest to be the origin. Physics lab. You guys take physics 1? Remember the bridge and the bicep experiment in Dr. Bogdan's class? Very first experiment, or one of the later, when you do torque, I think she did it November-ish. She talks about the torque around the elbow, force exerted by the bicep, acting as an attachment point down here, pulling upward. Same problem. Hold the weight out from your shoulder. What's the torque on your shoulder? Well, the weight is pulling straight down. I need to know the angle I make with the side of my body. Where is it? Where's the torque maximized? I got to do rotator cuff rehab. This is what I'm stressing on.
You just walk. You want to actually do it, but just like this step.
I hope so. What is it?
It's like it gives you 2 equations and a part.
So do the particles collide.
And
So-
then the second part is the pass and the second.
Okay. It's actually easier to do the second part first. I know that's crazy, right?
Nothing.
Well, that's okay. We can do they collide. It's the same idea. So do the 2 particles hit? Well, the 2 particles hit if the paths have the same point at the same time. So, first equation,
P squared 2Q.
I'll call that R1 of T. What's R2?
1 plus 2T, 1 plus 6T, and 1 plus 14T.
Okay, I was just evil and decided to change the letter for that one. Make it an S instead of a T. Why? Because I want to think of them as separate ideas. This curve on the left, R1 is operating in T. This curve on the right is operating in S. But here's the fun part. We talked about 2 lines intersecting, didn't we? How did we figure out if 2 lines cross? Well, they have to have the same X, the same Y, and the same Z, right? They have to have the same X, the same Y, and the same Z. Then that has to be true, doesn't it? You have 3 equations in 2 variables. This is an overdetermined system. To steal again, notation from linear algebra. This is too many equations and too many variables. So pick 2 of them. I want to do first and third. And the only reason I want to do first and third is because that's got the highest power on it, but the first one has the smallest power on it. So if I put those together, I'll get a cubic equation. And then I can solve that. And that'll give me an S value. Because I'll take this.
Can you do the first and second first?
Absolutely, but I might miss some information. Because when I solve a quadratic equation, I have 2 options. When I solve a cubic equation, I get 3. So while you can definitely solve the first and the second together, I think you'll learn more if you do the first and the third. But you solve that, you get an S value out of this, right? You put this over here, you get an equation S, you get some S. You also get a T once you have an S, don't you? Then you go to the other equation and you say, if I put that T and that S, does it work in the third equation? If it does, then they're at the same point, aren't they? And that would mean that the paths cross.
And when you get two S's, you have to.
I have to check both of them. And that's why I said I should do the third equation, because if I get three S's, I have to check all three of them. But that just tells me that the two curves cross each other. The next question is, do the actual particles hit each other? Did you drive here this morning? You walked here. Okay. You walked up from A-Lot, up through A-Lot? I went through A-Lot this morning. I didn't hit you, did I? I drove my car through A-Lot. You walked through A-Lot. We both went on the same path at different times. So the question not only is, do I arrive at the same point, but do I do it at the same time? Is there a t value that matches that s value? So when you do your s's and t's, do any of them come out to be the same? And I'm pretty sure that the paths just cross each other and they don't actually hit. Because they got to the same spot, but they got there at two different times. But I only know that they get to the same spot if it matches, if it works here, and it works here. Otherwise, those two paths don't even cross. They're askew from one another.
Why would the articles collide first?
Uh-huh.
Could I just do it where I set the t, like, the x's equal to each other? And then, like, for their t equations, like t equals 1 plus 2t, and then plug that t into the y equation, so. T
Then you get
squared-
something in t squared.
And then, yeah, but I would get like, that their t, like, the left side isn't equal to the right side.
That's my problem, is because all of a sudden you've got two different ways of thinking about t, right? And that makes me twitchy. So maybe if you call this one T1 and this one T2, so you knew they were different time ideas, right? We're measuring the clock on the first person's car and the clock on the second person's car. And ideally, those clocks started at the same time, but maybe I drive slower and this person drives faster, so they cross the road in front of me. We went through the same spot, but we didn't hit each other. I will say this one takes a little more algebra because we're so used to just taking whatever variable they give me. This idea of changing variables isn't automatic. But I really need to think of what's going on the first path and what's going on the second path as separate from one another. And that's the reason why I chose to use two different letters. Back in Calc 1, we did a problem where we threw a ball off a cliff. The ball went up, and we figured out what time it hit the ground. And then there was another part to that problem where we threw another ball a second later. We figured out that equation. Now we had to change the time value, right? And so we used two different letters. It's that same idea. That's back in chapter 3, I believe. More questions? Yes, yeah. 61. Find an equation consisting of all points equidistant from two given points. Okay. Here's point 1, here's point 2. Yes? Halfway between them, how do I find that spot? There are lots of ways to do this. Take the middle, add them together, divide by 2. I could also think about the line segment between them, right? And that would be this, where R0 is the vector that points at one of these points. And the direction vector goes from the one I pointed at to the other one. So I could say use 0, P1 plus T, P1, P2. Yes? And if I plug in T equals a half, I'm halfway between them. Now, I know a point. My goal is to find a plane, yes? To find a plane, I need a point on the plane. We have one. And I need the direction perpendicular to the plane. The vector P1, P2 is perpendicular to my plane. Because every point, no matter how far up or down I go, as long as that makes a right angle, the distance from here to here is the same as the distance from here to here. So once I actually have the point, I then get my normal vector, which turns out to be that vector right there. More questions? Okay, I need to show you two things before we leave. Thing number one, this is the front cover of the exam. One side of one standard 3x5 card. If you don't have one, we have a bunch of them over in the Enrichment Center. But I'm telling you, you can write all sorts of formulas. All of my calc classes got a formula sheet, didn't you? For other stuff we already did. Okay. I'll give you this stuff as well. That's the last page of the exam. So all of those trig derivatives, you get them again. So you don't have to put those on your note card. One other thing. I have been told of the potential for absolutely crap weather tomorrow. It's supposed to start raining tonight and potentially ice over. They said it should be over by about 4 in the morning. But that means that coming in tomorrow morning might really be dangerous. So I'm going to find out what the weather looks like tomorrow morning. And if the weather sucks, we'll do class with me at home, just like this, only I'll be talking over Zoom and you'll be able to, I'll send you the link at the start of the class time so that we'll have the ability to do it. But that means, since the homework is due, if I'm not physically on campus, you'll have to scan it and send it to me. I'm hoping to get here because this class tomorrow is at 1 o'clock in the afternoon. I'm hoping that the roads will be good enough by then because it's supposed to be 50 tomorrow. After all this crap blows through and we get ugly tonight, it's supposed to be nice tomorrow. So we'll see. But forewarned is forearmed. Somebody please tell Nora. I hope she'll watch the recording, Nora. Otherwise, I will see you all tomorrow. If you've got questions, come bug me this afternoon in office hours.